Okay, good day. This is Math 140 College Algebra. I'm Professor McCully, and this is the presentation for Lesson 5.1 on complex zeros. Let's get to it. Our learning goals, we're going to use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. And then we are going to conjugate pairs of complex zeros. And then we're going to find zeros of polynomials by factoring. So I've got a couple of definitions that I'd like to talk about first. First, the fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the complex number system. So if you have a polynomial, it has to have at least one 0 in the complex number system. Then, piggybacking off of that theorem, we have this linear factorization theorem, which expands on the first theorem by saying this: if f of x is a polynomial of degree n where n is greater than 0, then f has precisely n linear factors where f of x is equal to some constant a sub n times this product of linear factors where c1, c2, all the way up to cn are a list of complex numbers. Some of them can be real, some of them can be imaginary, some of them can be fully complex, where you have a plus bi. Finally, complex zeros must occur in conjugate pairs. If we let f of x be a polynomial that has specifically real coefficients, and we are given that a plus bi, where b is not equal to 0, is a 0 of the function, then its conjugate, a minus bi, must also be a 0 for the function. So, just as a quick example, if I were to make up a polynomial function, say f of x is equal to 3x to the fourth minus 2x squared plus 6x minus, say, 3. And we were given that 1 minus 3i is a 0. Now, I don't know if it is because I'm just making it up, but to illustrate this complex zeros occur in conjugate pairs rule, since each of these coefficients are real numbers, you don't see any i's, they're all integers. If I am given an imaginary 0, then I know that 1 plus 3i must also be a 0. And again, the reason is that when you multiply conjugates together, you'll get a whole real number. And I will show you an example of that here in a moment. Our first example, though, is to find all of the zeros of the function and then write the polynomial as a product of linear factors. We're actually going to do that backwards. We're going to find the product of linear factors first and then find the zeros. And the reason that we're going to do that is because this thing is in quadratic form. And it has the form y equal to ax squared plus bx plus c, where we have a constant. We have that constant, it's 100, and the degree of the leading term is twice as big as the degree of the middle term, and so 4 is twice as big as 2. So this thing will factor if I can find two factors of 100 that add up to negative 29. And that's pretty easy because negative 4 times negative 25 is negative 100. So I get x squared minus 25 times x squared minus 4. And if you multiply that out, you'll get the original. And both of these factors are differences of squares. So we have both of those in the form a squared minus b squared is equal to a minus b times a plus b. So our a squared in both cases are x, and our b squared in the first case is 25, and in the second case it's 4. So our value for b will be 5 and 2 respectively. So this thing is going to factor into x minus 5, x plus 5, and then x minus 2, x plus 2. Now this is our, well, I suppose if I write it as f of x here, this is my product, product, of linear factors. So since I'm doing it backwards, I'm going to label both of them so that whoever would be grading this particular problem will know which is which. And then my list of zeros will be x equals, and then I'm just going to figure out what makes each of these factors 0. So 5 makes the first factor 0, negative 5 makes the second factor 0, 2 makes the third factor 0, and negative 2 makes the fourth factor 0. We'll put a box around that, and we'll say we're done. Next example, it says find all of the zeros of the following function, then write the polynomial as a product of linear factors. All right, so if I look at this thing, I might try and factor it. I'll look at this thing. I have 1, 2, 3, 4 factors. I might try grouping, but if I group the first two, I can factor out a 2, and then I'll have 4 and 7. And if I factor out, and I could factor out maybe a 9, I'd have 2 and 1. And so that's not going to work. Factoring by grouping isn't going to work. I don't have a cubic formula, so I have to kind of go to the rational root test. So I'll start with my list of p, and the factors of negative 9, so the constant term. The factors of the constant term are going to be the factors listed in p. And so I'll have plus or minus 1, plus or minus 3, and then plus or minus 9. And then my values for q will be the factors of the leading term, will be the factors of the leading coefficient. So I'll have plus or minus 1, plus or minus 2, plus or minus 4, and then plus or minus 8. And so my factors p over q will be all of these over each of one of those. So 1, 3, and 9 over 1 will be plus or minus 1, plus or minus 3, and then plus or minus 9. And then 1, 3, and 9 over 2 will be plus or minus 1/2, plus or minus 3/2, and then plus or minus 9/2. And then everything over 4 will be plus or minus 1/4, plus or minus 3/4, and then plus or minus 9/4. And then everything over 8, so plus or minus 1/8, plus or minus 3/8, and then plus or minus 9/8. Now, that's a long list, so I'm going to use my graphing calculator to reduce the number of possibilities. If I look here, here's my original, and I hit graph. Now the original is a third degree polynomial, so it has to have exactly 3 zeros in the complex numbers. When I look at the graph, it looks as if it only has 1 real 0. That means the other 2, which will be in conjugate pairs. Why? Because all of the coefficients are real numbers. Those 2 imaginary zeros will be conjugate pairs of each other. Now I have to decide which rational zeros is most likely to be this one. Has to be between 1, or it has to be between 0 and 1, and a little bit closer to 1. So if I look at this list, all of these are 1 or bigger, so those won't work. Half is smaller than 1, or smaller than a half. Oh, that's actually a half. That's too small. That's more than 1. That's more than 1. That's less than a half. This is more than 1. That's way less than a half. That's less than a half, and that's more than 1. So the only one that's realistic is this 3/4. So I'm going to divide that out by using synthetic division. I'll go 8, negative 14, 18, and then negative 9, and I'll put 3 over 4 here. Now I'll bring down my 8. Now 3/4 of 8. You can do this by dividing and then multiplying. So 8 divided by 4 is 2, and then 2 times 3 will give me a 6. Negative 14 and 6 will be negative 8, and 3/4 times 8 we already know is 6, but since I'm multiplying by a negative, it'll be negative 6. 18 and negative 6 is 12, and then we'll do the same thing for the 12. We'll go 12 divided by 4 is 3, and then 3 times 3 is 9, and 9 and negative 9 is going to be 0. All right, so my first factor will be x minus 3 over 4. Now I divided out an x from a third degree polynomial, So this result will be 8x squared minus 8x plus 12. Now I see that this all has a common factor. I could bring that 4 out and I'll have 2x squared minus 2x plus 3. And if I move that 4 up to here and just cancel it out there, this first factor becomes 4x minus 3. I could put my parentheses around that. This is my first factor. Now again, I don't think that I am going to have any other real zeros because it only crosses the x-axis once. Since it's a quadratic and I don't think it's going to have real zeros, I am going to use the quadratic formula. And so when I go to do that, I need to find my b. So x is equal to negative 2, that'll be 2, plus or minus the square root of b squared, so negative 2 squared, minus 4 times a, which is 2, times c, which is 3, all over 2 times a, which is 2. Now, when I reduce this, I'll have my 2 plus or minus. Negative 2 squared is 4. Negative 4 times 2 is negative 8. Negative 8 times 3 is negative 24. 4 minus 24 is the square root of negative 20 all over 4. Now, negative 20, because of the negative, I'll have an I. And then 4 divides 25 times. So if I take the square root of 4 off 2, so this becomes 2 plus or minus 2i square root of 5 all over 4. And I can divide a 2 out of all of those terms. 2 divided by 2 is 1. 2i square root of 5 divided by 2 is just I square root of 5. And then 4 divided by 2 is 2. Now these are my remaining zeros. Now this thing here asks us to write as a product of linear factors. So f of x, the first factor was 4x minus 3. And then I'm just going to make factors out of these remaining zeros. So if it was just 3, you'd go x minus 3. And if it was negative 3 was a 0, you go x plus 3. So I'm just going to do the same thing here and go x minus 1 plus I square root of 5 all over 2. And then I'll go x minus 1 minus I square root of 5 all over 2. And that is my list of linear factors. 2 are imaginary, 1 is real. I feel confident in that because our graph only crosses the x-axis once. Okay, last example. Given that 3i is a 0 of the following function, find the remaining zeros of the function. So they're telling us that since 3i is a 0, we know that negative 3i must be a 0. And we know that because all of those coefficients are real, and since all of the coefficients are real, any imaginary 0 must occur with its conjugate pair. So I'm going to divide these two out, and what will be left will be the last 0 of that function. It'll actually be the last factor. So leading coefficients, I'll go 1, 1, 9, and then 9. And we're going to divide out 3i. I'll bring down my 1. 1 times 3i is 3i. 1 plus 3i is 1 plus 3i. Now when I go 3i times this 1 plus 3i, I've got to distribute. So 3i times 1 is 3i. 3i times 3i will be 9i squared. Now remember, I squared is negative 1. And so negative 1 times 9 will be negative 9. And when I add negative 9 to, when I add 9 plus negative 9 plus 3i, the 9's cancel. And I have 3i. And then 3i times 3i is again negative 9. I'll have a 0. We know because of the conjugate pairs that negative 3i must also be a 0. When I bring down the 1, 1 times negative 3i is negative 3i. 1 plus 3i minus 3i will just be 1. And then 1 times negative 3i is negative 3i. That'll give me 0. And so this remaining factor will be x plus 1. Now this thing asks us to find the remaining zeros of the function. The question before us asked for a product of linear factors. This is what a product of linear factors. The list of zeros are just what makes each of those factors 0. So our remaining zeros are going to be x equals, they gave us 3i, so the ones that we found were negative 3i, and then whatever makes this equal to 0, x equal to negative 1, so negative 1 is our remaining zeros, plural. We'll put a box around that, and we'll say that is it for today. And so, the Marvel fun fact of the day, in Spider-Man Far From Home, Mysterio states that this is Earth 616, which is the main Earth timeline in Marvel Comics. The reason Marvel writers chose the number 616 was to show that our Earth has no particular significance to it. Although I think it's pretty special. Well, that's all I got for today, folks. Have a good day. Goodbye.